inherent. So I'm at the moment talking about application of mathematics. Let I tell you, this is a very vast area. I'm at the moment, of course, talking only a thread of it. You see what? Application of fundamental theorem of algebra. One application I have already mentioned, because the this symposium and this is pertaining to complex analysis. Therefore, my applications are also pertaining to complex analysis. Otherwise, you see, we can talk about mathematics and the application of mathematics in general. My first application, which I gave you in my last lecture, I come to the second lecture. You see, the matrix A was 2 cross 2. I mentioned even at that time that the matrix can be even n cross n. And if in particular, if the matrix is 1 cross 1, then the application, we can talk of a beautiful application. And that application I read before you. Suppose that you want to open a saving account and you shop around for the best possible, best available interest rate. You learn that discrete bank pays 7% annual interest compounded annually. Its competitor, the Bank of Continuity, offers 6% annual interest compounded annually. Everything else being equal, where should you open the account? This you can see, beautiful application of mathematics. Okay, let us see. You can see same thing. See, let us examine what will happen to your investment at the two banks. At discrete bank, the balance grows by 7% each year if no deposits or withdrawal are made. Then what happens? New balance would be equal to old balance plus interest after a year. And that means if the new balance is x of t plus 1, that would be equal to xt old balance plus 0.07 xt. Right? Then that means xt plus 1 is equal to 1.07 xt. This is discrete bank. This equation describes a discrete linear dynamical system with one component. Right? Then the balance after t years would be, see, every time when this happens, the balance after t years would be xt would become equal to 1.07 whole raised to power t into x0. This would be your discrete bank balance after t years. The balance grows exponentially with time, of course, exponentially because it is power. At the bank of continuity, now come to at the bank of continuity. By the definition of continuous compounding, the balance xt grows at an instantaneous rate of 6% of the interest rate is less, 6% of the current balance. It means because it is a matter of continuity, it grows every time. So this becomes a matter of differential equation. So it would be, the current balance would be dx by dt would be equal to 6% of balance xt. That is, dx by dt is equal to 0.06 into xt. Look at one equation. If the xt would be equal to 1.07 t into x0, and this would be dx dt. dx by dt is equal to 0.06 of xt. We can solve this about differential equation. This is simple differential first order ordinary differential equation. Dx by xt is equal to 0.06 into dt, log of etc. and xt. Therefore, dx by x is equal to 0.06 dt. Integrating both sides, we get log of x is equal to 0.06 t plus some constant. After solving this differential equation and putting t is equal to 0, it would be log of x0. Log of x0 would come over here, and therefore that would be multiplied, and therefore, see, for some constant k, exponenting gives x is equal to c into e raised to power 0.06 t. This would be balance after t years in bank of continuity, and that would be xt would be equal to 0.07 raised to power t. See in that 0.07 raised to power t, 1.07 raised to power t into x0. These are the two balance after t years, and we can compare. What we can compare? Where c is equal to e raised to power k is equal to x0. Putting t is equal to 0, c would be the value of c would be x0. Which bank offers the better deal? We have to compare the exponential function 1.07t and e raised to power 0.06t. Using a calculator, we compute e raised to power 0.06t, that is 1.0618 raised to power t. To see that discrete bank offers a better deal, because see the value of that constant x0 would be less than that. The extra interest from continuous compounding does not make up for the 1 point difference in the nominal rate. So nominal interest rate. So that discrete gives you. Look at the application again. The application fundamental theorem of now. See the analytic function and how study is carried. I'll let you know. Talking about zeros of analytic functions, that I will confine to. I will address to zeros of analytic function, but how the study using, of course, fundamental theorem of algebra is carried to the study of analytic function in complex analysis. P z, once again, I come back to my original polynomial, which I began with. If P z is equal to Zn plus an minus 1, minus 1 plus a1z plus a naught is a polynomial over the field of complex number, over the set C is a complex number. Then fundamental theorem of algebra, there exists complex number alpha 1, alpha 2, alpha n, not necessarily distinct, that Pz can be written as z minus alpha 1 into z minus alpha 2 into z minus alpha n. This I mentioned you earlier. Any polynomial, non-constant polynomial Pz of analytic can be expressed as z minus alpha 1 into z minus alpha 2, z minus alpha n, where alpha 1, alpha 2, alpha n are complex numbers. Alpha I is called zero the polynomial. See that these zeros are scattered. Scattered means, alpha 1 is over here, the alpha 2 would be over here, there would be alpha 1 minus alpha 2 mod would be 0. Like that, these zeros are scattered. See, only that, after this, I was telling myself, visible to everyone. If alpha I is equal to alpha is the 0 of P that repeated m times m less than or equal to n, then we can write P that is equal to z minus alpha raised to power m into qz, where qz is a polynomial. Which question arises? Which question? Now I have moved this slide. Question is, can we say such a thing for analytic function? Meaning, can we say, see, polynomials are, of course, I'll let you know, they are analytic functions. What is an analytic function? I'll tell. My question is, can we say the same thing for analytic functions? This is the question. See, what is an analytic function in a disk? First, in a disk. Then you can extend this to an open set. I'll let you know orally, of course, but I require, for my discussion, I require only analytic function in a disk. I'll pertain only to disk, but the definition of analytic function can be carried over any open set. See, open set also, I'll let you know why open set. The definition says let D be equal to all those Z belonging to C, such that Z minus A mod is less than R, be an open disk in complex plane. A function from D to C is said to be analytic in D if f is differentiable in D, meaning thereby f is differentiable at every point of D. Now, f is said to be analytic in an open set if f is analytic at every point of D. What is meant by saying f is analytic at every point of D? Meaning thereby F is analytic in a neighborhood around Z naught. That is, there exists a disk around Z naught, that F is analytic. F is differentiable at every point of the disk. I remember when I was perhaps long back, I was in MSc final, you know. When I taught, when I learned complex analysis, my teacher was telling me the definition of analyticity, differentiability, etc., etc. And perhaps one of my classmates asked the teacher this question: Sir, when you define analyticity or differentiability, you always take an open interval. Eh? Why not a closed interval, etc., etc.? Why should we not take it? And you take always like the answer, that great teacher answered that, look, when we are talking about differentiability, when we are talking about continuity, we always take this notion in the limit form, and that is a disk around the point, because differentiability, continuity, etc. is a local concept, meaning thereby differentiability at a point and say continuity at a point. When we talk of differentiability or continuity, we virtually are working in a neighborhood around that point, and therefore I take always the definition of analyticity or differentiability in an open set. That was the answer, which of course satisfied everybody, and that was the right, correct answer. Right. I come once again, that we say f dash z exists at every point z in D. F is said to be analytic at a point A if it is analytic in a neighborhood of A. That is a disk around A. See, because neighborhood in the set of complex plane, they are nothing but disk, open disk. See? So, but the definition can be extended to see any space Rn, etc., etc., etc. Observation 1. If F is analytic in D, then it is continuous in D. You can see when F dash Z exists, then you see it is continuous also. Why? Because Fz minus Fz naught is equal to Fz minus Fz naught divided by Z minus Z naught into Z minus Z naught, Z naught equal to Z naught. When I take the limit, the right hand side tends to 0. That means limit of Fz minus Fz naught when Z tends to Z naught is equal to 0. That means limit of Fz when Z tends to Z naught is equal to Fz naught. That means F is continuous. However, you see, this result, but F is analytic at every say. However, the converse is not true. For example, if Fz is equal to mod Z square, this is, we can see, and if you ask, okay, I'll tell you also, see that this is differentiable only at Z is equal to 0. This is not differentiable anywhere else. At Z is equal to 0, it is very simple to see, because Fz minus F0 is F0. So Fz divided by Z is equal to Z mod square divided by Z when Z is not equal to 0. And see, this means Z mod square can be written as Z into Z bar. So Fz by Z will become only equal to Z bar. When Z tends to 0, it tends to 0. But the converse is not true. By taking see Fz minus Fz naught, but it see at any other point Z not equal to 0, it is not differentiable because limit won't exist. Next observation, very strange one, Cauchy-Riemann equation. You see, whenever, if F is analytic in D and Fz is equal to Uxy, real value, real part and imaginary part, I Vxy, then U and V admit first order partial derivatives, Ux, Uy, Vx, Vy. Because U and V, they are functions of two variables. U and V will admit of first order partial derivative at that point, satisfying Ux is equal to Vy and Vx is equal to minus Uy. These equations are called Cauchy-Riemann equations. That is U and V, real and imaginary part of analytic function. They satisfy Cauchy-Riemann equation. But you see, however, these are called Cauchy-Riemann equations. However, Cauchy-Riemann equations are only necessary but not sufficient condition for a function to be analytic at a point. For example, if I consider the function f, okay, if f is analytic at a point, then CR equation C and f z is equal to u plus iv, real and imaginary part. Then it's C u and v admit of first order partial derivatives ux, uy, vx, vy at that point, and satisfying ux is equal to vy and vx is equal to minus uy. These are called Cauchy-Riemann equations. Cauchy-Riemann equations are only necessary but not sufficient condition for a function to be analytic. For example, if fz is equal to x cube into 1 plus I minus y cube into 1 minus I over x square plus y square, if z is not equal to 0 and f0 is equal to 0, if z is equal to 0, and then this for this function CR equations are satisfied at origin, but f is not differentiable at origin. This is what I was telling you. See, I should I be should I continue further? Voice is audible, right?
Your voice is
Voice,
audible, but screen is not visible.
voice is
PPT is not
audible.
visible.
Yes, sir. You may continue, sir. Please.
Okay.
Yes,
Voice is
audible, sir.
audible.
Audible.
Now screen is visible.
Audible, sir, PPT.
PPT is audible
Yes,
now.
sir. Yes, sir. PPT audible.
My next
Visible, sir.
observation, Taylor's theorem, right? Do you remember that such a result is true in say real variables also? If f is analytic in DAR, DAR is the again open disk with center A and radius R, then fz can be expressed as a n z minus a raised to power n and going from 0 to infinity for all z belonging to DAR. That means this is expressed as a power series, and since fz is equal to that, that means the radius of convergence of this power series is greater than or equal to r. This means that thing. See. Next observation. See, if f is differentiable once at every point in an open disk D, then it is differentiable at every point of D. Look, such a strange result, which is not true in case of real variables. That if f is differentiable once at every point in an open disk D, then it is not just once differentiable, it is infinitely differentiable at every point of T. Such a result is not true for real valued functions of real variables. For example, if I consider the function fx is equal to x cube sine 1 by x for x is not equal to 0 and f0 is equal to 0, then f is differentiable for each real number x. But f dash is not differentiable at x equal to 0. Such a result is not true in case of real analysis, in complex analysis. In real analysis, we can find a function which is differentiable at every point at every real number, but its first order derivative is not differentiable. See, you can take the function. Did I not give? Yes, this is fx is equal to x cube sine 1 by x, where x not equal to 0 and f0 is equal to 0. This function is differentiable. Why? Because what is f dash x? F dash x is equal to minus x cos 1 by x plus 3x square sine 1 by x for x not equal to 0 and f dash 0 is equal to 0. This is not given in PPT. I am just telling you that f dash x would be equal to see minus x cos 1 by x plus 3x square sine 1 by x for x not equal to 0 and f dash 0 is equal to 0. And this function f dash, you can see what this is not differentiable. Although x dash is continuous, f dash is continuous. Next definition. Now I come to zeros of the analytic function. Definition. That f from D I am taking to be disk. It can be even, C any open set, but I am taking disk. That f from D to C be an analytic function, where D is equal to this disk with center A and radius R. Then f is said to have थोड़ा water ला दो, ये पड़ा है पानी. Then f is said, ये पानी दे. When f is said to have a 0 of order m at z is equal to a, if fa is equal to f dash a is equal to f m minus 1a is equal to 0, all these up to m minus 1 derivative at a is equal to 0, and fma is not equal to 0. For m equal to 1, m equal to 1 means fa and f dash a, this is equal, for m equal to 1, that means fa. For m equal to 1, a is called a simple 0 of m. Right? My next observation. Suppose f is analytic in this disk, then a is a 0 of order m if and only if fz is equal to z minus a raised to power m gz, g being analytic in D and ga is not equal to 0. Let me have a remark over this observation. Do you feel that this is the same as we had obtained in polynomials? You see that a was a 0 of order m of the polynomial pz if pz is equal to z minus a raised to power m into qz, where q of a is not equal to 0. This is same thing. See, the study is carried to analytic functions like that. What exactly they prove? It is a simple proof using, of course, Taylor's theorem, that suppose because f is analytic in D, therefore fz is a and z minus a raised to power n, and going from 0 to infinity for each z in D, where an by Taylor's theorem, an is equal to fna by factorial n and greater than or equal to 0. Suppose that a is a 0 of order m. When a is a 0 of order m, this means fa is equal to 0, f dash a is equal to 0, fm minus 1 a is equal to 0, and fm a is not equal to 0, meaning thereby a naught is 0, a1 is 0, up to am minus 1 is equal to 0, and and am is not equal to 0. This means therefore fz is equal to an z minus a raised to power n from m to infinity, where am is not equal to 0. Which from here I can take z minus a raised to power m common from this. This is equal to z minus a raised to power m, and going from 0 to infinity, a of n plus m into z minus a raised to power m, and going from 0 to infinity once again, because it would begin from am plus 1, am plus 2, etc., like that. That means fz is equal to z minus a raised to power m into z and gz, where am is equal to ga, and that is not equal to 0, and g is analytic in D. This proves one part. Conversely, let fz be equal to z minus a raised to power m, where g is analytic in D and ga is not equal to 0. That means from here, when I obtain fa, it is 0. When I obtain f dash a, f dash z is equal to m into z minus a raised to power m minus 1 into gz, plus g dash z into z minus a raised to power m. So f dash a, when I put z equal to a, it would be 0, and so on, so on, so on. And f of mz would be equal to factorial f of ma is factorial m into ga, which is not equal to 0, and fa is equal to f dash a is equal to fm minus 1a is equal to 0. That means z is equal to a. This is a 0 of order m. You see what I am doing? I am comparing the whatever was true in polynomials. I am carrying the whole thing to analytic function. One part I have already carried. Which part I have carried? That if z is equal to a, firstly is a 0 of polynomial of order m, then pz is equal to z minus a raised to power m into gz, ga is not equal to 0. This is carried to fz is equal to z minus a raised to power m into gz, where g of a is not equal to 0, and this is if and only. Second part which I observed was zeros were scattered. Zeros were scattered, one zero is away from the other, and so on, so on, so on. This I will now try to carry on to analytic function. Let us see my next observation. Observation next is zeros of an analytic function are isolated. Meaning thereby what? Meaning thereby that if there is some zero of analytic function of course, a non-constant analytic function, then I can always find a neighborhood around that point where no other zero lies. This is meant by saying isolated. And a zero is said to be isolated if we can find, if it is a zero, firstly. Secondly, if we can find a neighborhood around that zero such that there is no other zero of the function f in that neighborhood. This is meant by saying isolated. So I am not trying to prove that zeros of analytic function, they are proof. Suppose that f where d is equal to this, please take this as open this. It is to remove that closed one, equality. Let z be d be equal to all those that belong to C, such that z minus z not mod is less than r, and co is 0. Let suppose that f is analytic in D, where D is this, and let A belong to D 0 f. See, if this it is 0. That is what, and this, because it belongs to D is an open, therefore this one around it, such all z minus A mod less than s is contained. Now s in D, the function is differentiable at every point, and is for 0, and A is a 0, and therefore function can be expressed by Taylor's theorem. Fz is equal to summation and going from 0 to infinity and z minus A power n for all those that belong to D1. Now suppose that A is 0 order n, means Fz is equal to z minus A raised to m in the last observation. Ga equal to, and G is analytic. Therefore, is analytic is not 0. So there is epsilon which we can less as z for each in those that such that the Ga is not equal. Therefore, G is not equal to this so that minus A mod less than S. Therefore, for all those that such z minus A mod greater than 0 less than epsilon, Fz is equal to z minus A raised to power m into Gz, which is not equal to 0. Therefore, z is equal to A. This is an isolated 0. So, next observation. Let f be analytic in an open connected G of F. Let f be the set of all zeros of f in G. If f has limit point in G, then f is equal to 0. This observation, of course, if you carry that, if you think about that observation in the set in real analysis, that is not. But this is a strange observation. If f is analytic in an open connected set G of T, then let S be the set of zeros of f in G. If f has a limit point in G, then f is equal to 0. See, this result is not true in real analysis. This result says that in an open connected set, if the set of zeros have got limit point, then the function is identically equal to 0. This is that one, which I'll tell you. Well, I remember, see, long back it was perhaps in 80s, I asked a simple question while setting a complex analysis. I asked a simple question, is cos z a bounded function? Cosine of z, a bounded function. That was simple. Based upon these
Unbounded, sir.
And that has to be unbounded. So that's cause and so that was, and many other things. You can talk about function where can we talk about a function in an open connected circuit, say unit, where it is at half it is 0, at 1/3 it is 0, at 1/4 it is equal to 0, and of course f is non-constant. No, because if it is analytic throughout, if it is different, then and if the set of zeros of 1/3, 1/4, 1/5, etc., they got limit point the at D, which is disk open disk, then f should be identical equal. Come to that, there are many good observations. See, let's this observation. Let be analytic in open connect subset G C, and let S be set of zeros out of 50. If f is a limit function, then f is equal to 0. Then f is identical equal to 0. It is equal to 0. It is written. It is f is identical line. F is identically equal to 0. Let A in G be a limit point of f. Suppose then there exists a sequence of by definition of limit point. There exists a sequence. There exists a sequence. And there exists a sequence n, and this sequence n as converging to a f is continuous to n just okay, because f is a continuous function. Since n is equal to all n therefore is equal to 0. Therefore f is 0. Thus a is not an isolated 0 because f1 is 0, f2 is 0, f n is equal to 0. They are converted to a and converted to a. That means a is not an isolated 0. This is clear. A is not an isolated 0. When a is not isolated 0, what happens? There is analytic or f is equal to 0 for each element neighbor. B.
Clear, sir. Yes,
Should
sir.
Clear,
sir.
okay.
Clear, sir.
So therefore, either f is analytic, and therefore f is not analytic, or f is equal to 0 for each element in a neighborhood z such that z minus a mod is less than delta of a. As f is given to be analytic, therefore we have that there exists delta greater than 0 such that this neighborhood M, which is equal to all those z such that z minus a mod greater than less than delta is contained in G, and fz is equal to 0 for all z belonging to M. Okay, so we claim fz is equal to 0 for all z belonging to D. To prove this claim, we consider the set A, which is equal to all those z belong to G, such that z is a limit point of S, and we consider B, which is equal to all those z, such that z belonging to G, such that z doesn't belong to A. Complement of course, A. That means G is going to be equal to A union B. Clearly, G is equal to A union B, the way I have defined. See, also A is not empty as A belongs to A, which we have already proved. Also, A is an open set because for each belonging B belonging to A, there exists an epsilon greater than 0 such that fz is equal to 0 for each z such that z minus B mod is less than epsilon. Therefore, this neighborhood is contained in therefore, each element in this neighborhood is a limit point of S. Therefore, B belongs to all those z such that z minus B mod is less than epsilon is contained in A. So A is an open set because A is neighborhood of each of its points. Also, B is an open set because for each B belonging to B, there exists delta greater than 0 such that fz is not equal to 0 for each z belonging to this neighborhood z minus B mod less than delta. Therefore, B belongs to the neighborhood all those z such that z minus B mod less than delta is contained in B. Thus, B is also an open set. Look, A is an open set, B is an open set, G is connected set, G is equal to A union B, A is non-empty, we have already proved. Therefore, see, this is not possible if G is connected, and therefore one of them must be empty. A is not empty, therefore B has to be empty. Therefore, A becomes equal to G, and therefore this result. See, that B is an open set. As G is equal to A union B, A is non-empty, and G is connected. Therefore, B is equal to empty, and G therefore is equal to A. Therefore, each point in G is a limit point of S. Hence, f is identically equal to 0. It is typed as f is equal to 0. It should be 3 lines. F is identically equal to 0. Look, see next observation which we conclude from this, which we have proved just now. If f and g are analytic functions in an open connected set G, and fz is equal to gz is equal to 0 for each z belongs to G, then either f is identically equal to 0 or G is identical to 0. Please look at this observation a little more carefully and just see that such a result is not true in case of real analysis. We can find out, functions which is f is neither identically equal to 0 nor g is identically equal to 0. F and g both are differentiable at every point. Still, their product is always identically equal to 0. Such a result is not true in case of real analysis, but this result is true in case of complex analysis. Why? Because suppose f is not identically equal to 0, that means there exists some point z not belonging to see the function and the connected set G such that f of z naught is not equal to 0. Because f z naught is not equal to 0, then we can find out a neighborhood where f z naught, of course, but f z naught g z naught is not equal to 0, and therefore see z naught is 0 of G, but zeros are isolated. That means we can still find out a neighborhood smaller where f is not equal to 0 and g is not equal to 0. That means f z g z is not equal to 0. This is a contradiction. This is actually the proof. See, although the details can be written, but still, you see, if this result, please, I remark once again and say it specifically, such a result is not true in case of real analysis. It is true in case of complex analysis only that if f and g are analytic functions in an open connected subset G, and f z g z is identically equal to 0 for each z in G, then either f is identically equal to 0. Well, next observation. Let f be analytic in, say, this is unit disk, center with 0 and radius 1. Then if f of half is equal to 0, f of 1 by 3, all these are equal to 0, then f is identically equal to 0. Why? Because zeros of the function f, 1 by 2, 1 by 3, 1, etc., they have limit point 0 in the disk D, and therefore f should be identically equal to 0. This is the proof that you cannot find a non-zero function having these as zeros and which is analytic in the disk. In the end, well, we come to the end now. In the end, we give two more proofs of fundamental theorem of algebra based just on complex analysis. See, the first proof, my first proof is based upon Lively's theorem. Lively's theorem says that every bounded entire function is constant. I told you earlier also, bounded entire function, see, entire means that which is differentiable throughout the complex plane. You see, proof of FTA. So let Pz be equal to Zn plus An minus 1, Zn minus 1 plus so on, plus A1Z plus A naught be a non-constant polynomial. Let it possible. If fundamental theorem is not true, that means Pz is not equal to 0 for any z belongs to C. Then the function f defined by fz is equal to 1 by Pz is analytic throughout the complex plane. That means it is entire. When it is analytic throughout the complex plane, so it is entire. That, and also fz mod is equal to 1 by Pz mod is equal to this expression mod of Zn plus En minus 1 Zn minus 1 plus so on plus E1Z plus A naught mod, taking Zn common, Z mod n into 1 plus En minus 1 by Z plus so on plus An by Zn mod. This tends to 0 as Z mod tends to infinity, because the expression in the right hand side in the bracket tends to 1. Therefore, when this tends to 0, therefore for epsilon equal to 1, there exists r greater than 0 such that fz mod is less than 1 for all z satisfying z mod greater than r. Also, f is analytic, therefore it is continuous on the disk. This is closed bounded disk and hence it is bounded. So, therefore f is bounded. Therefore, there exists some m1 such that fz mod is less than or equal to m1 for all z satisfying z mod less than or equal to r, and if m is maximum of m1 and 1, then fz mod is less than or equal to m for all z belonging to C. Thus, f is bounded entire function and hence is constant by Liouville theorem. This gives that pz is a constant polynomial, which is a contradiction. Hence, therefore, there must exist some pz is equal to 0. See, every bounded entire function is constant. That means if there is non-constant entire function, that cannot be bounded. For example, cos z. For example, e raised power z. For example, sin z. For example, cos hyperbolic z, etc., etc., etc. There are many functions, you see, which are constant. See, one more observation, just for the sake of interest now. You know that, you see, 1 plus x raised to power m is equal to 1 plus m into x minus 1. This is not, there is no slide, therefore it is not, you see, about this, but I'm just telling you. 1 plus x raised to power m is equal to 1 plus mx plus m into m minus 1 by factorial 2 into x square and so on plus xm. This is true for real analysis. Can we extend the same to complex analysis? Same, looking at this result. My question, I'm asking you people, gentlemen, I'm asking you people. 1 plus x raised to power m for any integer, for any positive integer m is equal to 1 plus mx plus m into m minus 1 by factorial 2 into x square plus so on plus x raised to power m for all x belonging to R. Looking at this, I can say that this result must be true in complex also. How? If anybody can answer me.
Because this expression 1 plus x raised to the power m is binomial expansion, and condition is that the modulus of x should be less than 1.
Less than 1.
Yes, sir.
No,
Yes, sir.
for this condition, for this you need not have x mod to be less than 1.
Yes.
It is only when you have infinite series, only then you require x mod to be less than 1. It is true for any x. 1 plus x raised to power m is 1 plus mx plus m into m minus 1 by factorial 2 into x square plus xm. I tell you, my friends, please
Yes,
listen to me. Listen
Yes,
to
sir.
me.
Yes, sir. Yes, sir. Yes, sir.
You consider two functions. Fz is equal to 1 plus z raised to power m and gz is equal to 1 plus mz plus m into m minus 1 by factorial 2 into z square plus so on plus zm. These two are functions which are entire and they agree on real analysis, on real numbers because of this theorem. When the entire function they agree on reals, then they agree on complex also. This is what I have told there, when it has got a limit point, because fz minus gz, this is an analytic function which will have limit point in the set of real numbers, because on real numbers it is 0. Therefore f and g, f minus g is identically equal to 0. That is, f is identically equal to g. Therefore fz is equal to gz for all z belonging to C. That means 1 plus z raised to power m is equal to and that is 1 plus mz plus m into m minus 1 into z z square factorial divided by factorial 2 z square. Look, that is the proof. That is actually the proof. You see, look at that thing. See, whatever, you see these things, these are so-called applications of that theorem, which I told you. That is called identity theorem. When something agrees on a line, when these two entire functions agree on a line in a domain, then they agree on the whole domain in an open connected subset of the complex plane. If it is true, if it is a complex set of all complex numbers, they will agree on all complex numbers. This is proof, right? That is the proof, actually. You know. And next proof is based upon Roche's theorem, and I'll give you one interesting application of Roche's theorem also. If f and g are analytic within and on a simple closed rectifiable curve C, and gz mod is less than fz mod on C, then fz and fz plus gz have same number of zeros within C counted according to multiplicity.
45, 47, 447.
See, proof of fundamental theorem of algebra. See, based upon Roche theorem. Suppose Pz is equal to Zn plus An minus 1, Zn minus 1, plus so on, plus A1Z plus A naught be a non-constant polynomial. Then I divide this Pz into two functions. Take Fz is equal to Z raised to power n and Gz is equal to rest of it. An minus 1, Zn minus 1, plus so on, plus A1Z plus A naught. Then f and g both are analytic throughout. You see, these are polynomials. Both are analytic throughout. And take gz by fz. This is dividing by zn. It will become equal to an minus 1 by z plus an minus 2 by z square plus a naught by zn modulus. And this tends to 0 as z mod tends to infinity. Please take it as z mod tends to infinity. Therefore, there exists r greater than 0 because this is tending to 0. Therefore, there exists some r greater than 0 such that gz by fz mod is less than 1 for all z, satisfying z mod greater than r. Take any small r greater than r. Then on this closed curve, although z such that z mod is equal to r and c is equal to this, on C, gz mod is less than r because it is true for all z satisfying z mod greater than r. As g and b, g and f both are analytic in C, therefore fz plus gz and fz have same number of zeros within C, counted according to multiplicity by what? By Roche theorem. But what about fz? Fz is z raised to power n. It has got 0 of multiplicity n, but fz is equal to z raised to power n has n number of zeros at z is equal to 0. Therefore, fz plus gz, which becomes this polynomial, has n zeros within C. This proves what? This proves fundamental theorem of algebra. Look, what a beautiful application. But one more beautiful application I am going to tell. And this is, of course, where I would talk about the last application. Consider the polynomial z4 plus 3z plus 1. Please do not look at the slide. Look at me only. Z4 plus 3z plus 1. This is what? A polynomial. It is a polynomial of degree 4. What fundamental theorem of algebra says? It has got 4 zeros. The fundamental theorem of algebra gives only this application. But question is, can we give some more information about this polynomial? This is the question. Can we give some more application? This is given by Roche theorem. How? We take gz equal to 3. We take two cases. Take firstly gz equal to 3z plus 1 and fz equal to z raised to power 4. Then gz equal to 3z plus 1 is less than or equal to 3z mod plus 1, and that is strictly less than z mod 4 when z mod is equal to 2. Because you can see when z mod is equal to 2, it becomes 3 into 2 plus 1, 7, and z mod equal to that becomes 16. Therefore, by Roche theorem, fz and fz plus gz have same number of zeros in this disk. This is Roche theorem. But fz is equal to z raised to power 4, and see, this implies that all the 4 roots, they lie only this. Why? Because fz is equal to z raised to power 4 has got 0 of multiplicity 4 at origin, and therefore z4 plus 3z plus 1 will also have 4 0. This implies all the 4 roots lie in the disk, although that's at that. This is first information by Roche theorem. Second information, which supplements again fundamental theorem of algebra. Take gz is equal to z4 plus 1 and fz is equal to 3z. Then gz, fz both are of course analytic, wherever, because these are polynomials, no problem. Gz mod is equal to z4 plus 1 mod is less than or equal to z mod 4 plus 1, and that is less than fz when z mod is equal to 1, because that becomes equal to 3, fz mod becomes equal to 3, and that is equal to 2. So again we can apply Roche theorem. So from this we conclude that because fz mod is equal to 3, fz is equal to 3z has got only 1 0 at origin. Therefore, z4 plus 3z plus 1 also will have only one root in the open disk. So what is the information? Only one root lies in the disk, although that side has z mod less than 1, and the other 3 roots lie in this annular. This is extra information given by complex analysis Roche theorem in addition to fundamental theorem of algebra. Please, fundamental theorem of algebra plus the knowledge of Roche theorem at least gives us that where are the roots lying, what are the position of the roots. This is the information. We can have many more applications considering polynomials. You see, this is one while writing this lecture, this is one polynomial which I thought about. You can take the information regarding many polynomials. I don't say all the polynomials the information can be given, but see many polynomials. See about many polynomials we can have the information about Roche theorem and so on, and make our study simpler, easier, and good. Thank you very much. Thank you. And I ask you if there are questions, they are welcome. Any observation, any comment, any observation on any comment on my lecture, anything which you'd like to say, please, you are welcome.
Any questions, please? From the participant side, अगर आपके कोई प्रश्न है, you may ask.
क्या टाइम है?
Any questions? Yeah.
हाँ, ठीक है. Welcome. Please, I may not be able to answer. My friend, I may not be able to answer, but I'll try definitely.
Yes, Kamalji, please.
Yes, sir. Yes, sir. Yes, sir. I have no question, but as far as the experience sir has shown in their slides and their this is very good, sir, and we are very much you can say very thankful that they have given their valuable time, and definitely this will encourage us for our teaching, and we will try to reflect this in our teaching too. Thank you, sir.
My friend, we exist only for the students. Our life had been.
Thank you.
It is only for the students, See, I am telling you, at this age, at the age of 76, I find it very nice to talk to you people. Really, it is my good time. You see that I have passed with you. I thank you for all patient listening. Thanks everybody. I thank everybody, for the patient listening they have given to me, Please. But see, this example also, this is only creation of my mind. I have not seen any book, but I created on my own. You see, that Z4 plus 3Z plus 1, if I take, I can get this information using fundamental theorem of algebra and Roche theorem, etc., etc., etc. Like that. This is how I used to teach. I have experience of almost 50 years or so, you see, teaching undergraduate and graduate, postgraduate classes, and then MPhil student, PhD student, and so on, all those things. Well, this is part of life. Thank you very much. Thank you for all that.
Thank you, sir. Thank you, sir.
Excuse me,
Thank
sir.
हाँ विनोद जी,
Yes,
yes,
sir. Thanks, sir.
Hmm.
On the behalf of CPDHE and all participants, I would like to express my gratitude to our esteemed speaker, Professor S.C. Arora, for his informative talk on the topic Fundamental Theorems of Algebra, a very simple and interesting way.
I
Sir
have
has
great,
explained in detail
my friend.
fundamental theorem of algebra, its historical background, and its application in daily life, and also
My
give us a valuable suggestion. Thank you, sir, for giving us your
my
valuable
friend, I
time.
have
Thank you, sir.
greater sense of
Thank you, sir.
gratitude to each one of you.
Yes,
I
sir.
thank all of you for patient listening.
Yes, sir.
Well, I thank CPDHE
Yes,
for
sir.
asking me to speak on this topic, speak on mathematics, because that is my first love, and I would say that is my only love in life. I
Yes, sir.
love mathematics because if somebody talks to me about
Yes, sir.
mathematics, if I talk about mathematics, I go to a different plane in life. I go to heaven. You see, that is the thing. See, I always feel happy that I am born with mathematics,
Yes,
and
sir.
I pray to God in my if there is any chance of any other birth, please I should live in mathematics only. That is the thing. Thank you very much.
Thank you,
Thank you
sir.
so
Thank
much,
you
sir.
so much,
Thank
sir.
you.
thank you
Thank you.
sir,
Thank you, sir,
thank
for
you very
valuable
much,
time, sir.
बहुत बहुत
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.